Cool. All right, so welcome everyone to our talk, Reengineering Hyperlight in Rust. Before we get into specifics of what we're reengineering from or what Hyperlight is, I figured we would just, reintroduce ourselves. So I am Danilo, or Dan. As you know, I work at Microsoft. I'm one of the core maintainers for this Hyperlight project. I'm also the author of a book called Server-Side WebAssembly that I'm authoring with Manning. And on my free time, I like to play a lot of Super Smash Bros. I'm a competitive player. And I'm here with my colleague.
Hey everybody, my name is Ludvig. Just like Dan, I also work at Microsoft, and I'm a Hyperlight maintainer. But I'm not a book author, and I'm terrible at Smash. So that's it.
All right, with that out of the way, this is our agenda for today. We'll start off with some introduction. There we'll explain what Hyperlight is, sort of what the motivation behind it is. Then we'll go over our migration story to Rust. Then we have a couple of key transformations that our code base went through, technical deep dive that we want to cover. And finally, some key takeaways, mainly learnings and successes and challenges of the whole journey. Okay, so Ludvig, take it away.
But first, so what is Hyperlight? So Hyperlight is a lightweight, open source virtual machine manager or monitor, a VMM. And you might have seen that the title of this talk is Reengineering Microsoft's Hyperlight, but Hyperlight is actually now part of the CNCF as a sandbox project, and it was donated by Microsoft. And so Hyperlight is designed to be embedded within two applications instead of run separately as a standalone binary. And what makes Hyperlight special is its speed. So a Hyperlight VM only takes about 1 to 2 milliseconds to create from cold start to be up and running. And how this is done is inside the Hyperlight VM, we don't run any traditional operating system. And so this completely eliminates any time to boot of that. And so you can think of Hyperlight similar to other VMMs like Firecracker or Cloud Hypervisor, but Hyperlight focuses more on executing short-lived functions securely, whereas those other ones are more general purpose built for like general purpose guest OS workloads.
Okay, so why is Microsoft working on something like this? And rather than describing it myself, I figured I'll show a little snippet from Mark Rusinovich, who's Azure's CTO, and also the keynote speaker for this event, who you might just have heard this morning. So yeah, just a 1-minute video from MS Build where he introduced Hyperlight and spoke a little bit behind the motivation of why we have this.
Now, the ways that we keep our infrastructure very efficient is by tightly packing customers together. Either virtual machines, and that technology has been around for a long time. More recently, within the last decade, we've introduced hypervisor-based isolation for containers with Hyper-V. So you can see that in the middle. And those address traditional OS-based applications, containerized applications, but we really see a place for user-defined functions, small functions that will execute either in the network data plane, like on a front door service, or as a user-defined function sitting inside of a storage service. But we need to strongly isolate them as well. And WASM, while it has a great sandboxing technology and it's really got a great ecosystem around it, lacks the kind of isolation that we require for running a public cloud. So we've been...
All right, cool. Thank you, Mark. So main thing I want you to get, oops, I can move to the next slide. Okay, so main thing I want you to get off of that quick video is that one of the big motivators behind Hyperlight is cloud security. And specifically here, Mark talked about a couple of different modes of isolation. So here we have a graph. Vertically, we have trust in our isolation primitives, and horizontally, we have the attack surface. So we have process isolation, Hyperlight, and SFI, or software fault isolation, and WASM. So we'll go through them one by one and sort of justify their placing on this graph. On the rightmost side, to start off, we have process isolation. So what that means, and its placing on the graph, is that sort of midway through the trust in isolation primitive, meaning that we more or less trust it. But it has a massive attack surface. That's because when you say process isolation, you should think something that uses sort of kernel features to be isolated. So think C groups, namespaces, containers, where you leveraging like the Linux kernel, and so you have a big attack surface to work on. And a display of this is that just between 2022 and 2024, we had 7 big reported container breakout vulnerabilities. You can read more about them on the site, container security site. But main idea here is that, because you can break out of a container very easily, this is not suitable for multi-tenant architectures where we have multiple customers sharing the same infrastructure. Then next up, we have Hyperlight. So Hyperlight is at the very bottom of, or leftmost side, depending how you're looking at it, on the attack surface. That's because, like Ludvig mentioned, Hyperlight guests, they don't have an OS. So there's very little to work with in terms of where you can attack it from. So its interaction with a host is very restricted. We'll go over that in more detail later on. And the trust in the isolation primitive is very, very high. That's because Hyperlight leverages hypervisors for its isolation. So Mark in the video talked about Microsoft Hyper-V or MSHV. That's one of the backends that Hyperlight supports. We also have KVM. Essentially, what we're using these things for is to create an isolated memory region, configure the virtual machine state, create a vCPU, and then run the said vCPU. And we do all this via hardware virtualization extensions like Intel VTX and AMDV. And so these things have been around for a while, and they've been beta tested. And so this is something that we can trust that will run our code or untrusted code in a public cloud safely. Now, just for completion, the last one that we have on this graph is SFI and WASM. Sort of in the same place in terms of that attack surface. WASM, similar to Hyperlight, also uses this sort of capability-based model where you don't have access to the entire host. So the attack surface is pretty equivalent, but the trust is a little bit lower. That's because WASM is sort of the new kid on the block in some ways. And so the trust isn't quite there yet for us to run that on like Azure. Cool. So now you understand what Hyperlight is. You understand why we're working on Hyperlight, how it sort of compares to other different other isolation modes like process isolation, SFI, WASM. We are a RustConf, so let's look at some Rust code. If you're using Hyperlight and you want to isolate some guest code, this is how you'd start. So first step is you would create a uninitialized sandbox. And you do that by providing it with a guest binary. Again, this guest binary is some potentially untrusted code that can be ELF, but that can also be WebAssembly, if some sort of security in depth. Also JavaScript. For WebAssembly and JavaScript, we've done the work of actually running the, say, WebAssembly runtime, JavaScript runtime inside of Hyperlight. That's why you can run it there. But if not, if you want to just use an ELF, sort of like this example here, you use our specific Hyperlight guest APIs to have a guest that's specifically built to be run on Hyperlight. So again, it's not any workload because we don't have an OS in the guest. So once you have your guest, say your ELF binary, you provide it to the uninitialized sandbox, which will allocate some memory in the host. It will then load the guest binary onto that memory. If you provide some extra blob data, you can also load it at that step. Essentially, this is mainly just setting up the initial memory layout without actually going into the VM. Now, the next step that you have is you can register a host function. Just a reminder, Hyperlight guests, they don't have an OS, right? So if you want to run workloads that are a little more complex, the host has to specifically provide the functionality that you want the guest to have access to. In this case, we have this function, sleep for 5 seconds, which, as the name suggests, you'll sleep for 5 seconds. And these are essentially syscalls that the guest will then have access to via the Hyperlight guest API. Okay, once you have your uninitialized sandbox, you load a binary, you have your host functions, you can then evolve this uninitialized sandbox from this uninitialized state to a deinitialized state, or just what we're just calling sandbox here. And then you can call functions inside of this sandbox. Because in that evolve step, what we did is we actually went into the VM, so we did the first VM run. we set up some control registers. We set up, say, on KVM, the initial user space memory regions, set up the hypervisor partition, all that good stuff, to then be able to call into the host to run some sort of guest function. And like the comment says there, that must be defined in the guest binary. We don't have this code, the code for this function in the slides, but essentially this function is a function that's been registered with the API, and it then calls a host function to actually do that print operation, because the guest doesn't really have access to print or anything like that. Cool. So as I told you, this is a migration story to Rust. So Hyperlight wasn't always Rust. It started off as a C# prototype. And this is more or less what it looked like. And I say more or less in terms of, I wanted to get a similar example to what we had, but we don't have the registering host function here, but it's pretty equivalent. So let's walk through it to see what this looks like. Now, very first thing that we do is we have this using statement. This is because .NET or C#, it's a garbage collected language. And so with our struct here, or classes in C# sandbox, because with the sandbox we had to do marshal copies from the managed memory region to unmanaged, with using, it essentially allows you to dispose the memory after you're done, so that you have deterministic cleanup rather than eventual cleanup with the garbage collector. Cool. Now you have your sandbox, and here comes the step of guest functions and host functions. Essentially what we have here is we have that exposed methods class, which looks like this. Print output is your equivalent guest function. You see it takes a string, it returns an int. That's how the parameters are laid out, or parameter and return type. And then you have your host methods. So guest ones are equated to null, and host methods have an actual definition. And guest methods are set to null because in C# we actually do something pretty cool, which is this IL generation. So at runtime, we bind this guest function to this named value of print output, which will then, so we'll generate code to actually call into the guest, and we'll do all that behind the scenes with this type-safe way. And then next, you see this guest methods print output, and that, for all Rust developers here, it might look like a macro call, but it's not. That exclamation mark there is in C# called the null forgiving operator. Essentially us telling the compiler that, well, this looks null. It's not, because of all the IL generation that we did in just the previous step. Cool. So we called our guest function, and then we can do a console write line of the actual result, which in this case will be that end that we saw just in the previous slide. Okay, so we saw what Rust or Rust API looks like before. This is what C# or what the Rust API looks like now. This is what C# looked like before. So what motivated our migration from one to the other?
Right, so there are a couple of reasons we decided to migrate from .NET to Rust. And one of them is that writing a VMM such as Hyperlight requires a lot of systems-level programming. And so in its core, a Hyperlight VM is just a chunk of memory, and it's a chunk of unmanaged native memory, because we need to be able to map it into a VM. And as you might know, .NET uses a garbage collector. And while we can use unmanaged native memory from .NET, it's not one of the strong points of .NET. And mixing unmanaged and managed memory together often introduces a lot of complexity. It's hard to reason about what's unmanaged, what's not unmanaged, and you have to basically keep track of everything. So we find it's easier to just go with unmanaged memory altogether. And in addition, marshalling between unmanaged and managed memory can also add overhead in terms of performance if you're copying memory over. So another reason we decided to migrate from .NET to Rust is that Hyperlight is designed to be embedded within an application. Hyperlight is a library. Hyperlight does not run as a standalone process. That means that if somebody wants to depend on Hyperlight, and Hyperlight is written in .NET, then they would also bring in a runtime dependency on the .NET runtime. And for many of our potential users, that's just an immediate no-go. They don't want anything to do with the .NET runtime. And we found that many of our potential users are already writing native code like C or C++ or Rust. And so we want to meet our users where they're at already, basically.
Okay, then I guess the obvious one is performance. Again, .NET is a garbage collector language. For a lot of applications on Azure, that's just a no-go, something that we cannot use at all. And even more with Hyperlight, that has such a strong focus on performance, aside from the security side, just the performance also of having that boot in 1 to 2 milliseconds. Migrated from .NET to Rust, we got a pretty big jump in performance, which I'll show more in the key takeaway section of these slides. Okay, so maybe an obvious question is, considering all these previous requirements that we had, I feel like C and C++ would do an okay job at fulfilling them. But if you were in the keynote talk from Mark Rusinovich, you might know why we didn't do that. As reported by Matt Miller, Microsoft security engineer at the Blue Hat Security Conf, 70% of CVs at Microsoft are memory safety issues. So, and a lot of that stems from using languages that are memory unsafe, like C and C++. For large code bases at Microsoft, like Windows, are written mostly in C and C++, and those vulnerabilities come from a lot of that from that. And then also, this is a tweet from Mark Rusinovich saying, speaking of languages, it's time to halt any new projects in C and C++ and use Rust for those scenarios where a non-garbage collector language is required. So there's been a big push internally to use Rust instead of C and C++ when starting a new project, or in our case, when doing that migration from C# to Rust. So when evaluating our choices here, Rust just seemed pretty obvious choice to go with.
All right, so given those reasons for why we wanted to migrate to Rust, how did we actually do it? So we chose to go for a gradual migration strategy where we picked small parts of our .NET code, and we migrated those small parts into Rust, and then we interfaced between .NET and Rust using a C API, also written in Rust. And the main reason we chose to do this is that allows us to verify the behavior of a Rust implementation against the old .NET implementation, because we can reuse our .NET tests to exercise our Rust code using FFI. All right, so on a more detailed level, what does this look like in detail, calling Rust from .NET? Well, Rust makes it very easy to define a C API. All we have to do is specify that the crate type is just a C dynamic library. And that's all it takes for Cargo to produce a shared object file or a DLL. And then anything we want to export in this dynamic library, we just mark with the nomangle attribute along with the pub extern C as well to make sure it's using the C API. And that's it. And now we have a C API that calls into Rust. And then from the .NET side, what does this look like? Well, we can use the DLL import declaration right here, which we just give the name of our dynamic library. We put the declaration up on top of just a function declaration like this, and then calling the .NET function sandbox new, for example, down there, is just going to transparently call into the C API and into Rust for us. So that makes it very easy to call into Rust from .NET. Of course, you have to be careful with memory ownership and stuff like that as well.
Cool. So I hinted a little bit at this in the previous slide where I showed you what the API looked like with C#. But there's a lot of parallels between what in C# is idisposable and in Rust is drop. So again, you have this using statement where we have sandbox new. And this essentially is synthetic sugar to a try finally. So we create the sandbox, do some operations with it, and then finally dispose. And now depending on where you're sitting, you might not even be able to see this next code segment, but that's kind of the point. This is from the official Microsoft documentation on idisposable. And so what I want to say here is that it's really not trivial as it is sort of with implementing drop. we have the use of flag disposed, which is used in some implementations of dispose to check. There you're checking if dispose is set to true, and if it is, dispose is a no-op. You have specific APIs that you can leverage. In the first implementation of dispose, we called this GC suppress finalize. What even is that? And when comparing all this to drop, where you just take that mutable reference to self and you perform operations on that, is the comparison between this and this very non-trivial thing really shines. And this is error prone not only on the Hyperlight maintainer side but also the user side, right? Because people that are using Hyperlight then have to remember to use using so that your memory is properly disposed of, which is not the case with Rust, where when the variable just gets out of scope, drop gets called automatically. So we found a parallel between drop and nice-bolsable pretty cool, because drop is just way less error prone and more trivial to implement than disposable, which is nice.
All right, so like we mentioned before, Hyperlight focuses on executing guest functions inside a VM securely. But in order to do this, like you saw in Dan's example earlier, we need to know the guest function signature from the host. So that includes, we need to know the name of the guest function, we need to know the parameter it takes, the parameter types, and the return type. And historically, this has been pretty prone to error because this function signature needs to match both in the guest and in the host. Because remember, we have two different binaries running. We have one binary running on the host machine that's using the Hyperlight API, and then we have another guest binary running inside the Hyperlight VM. And these two need to agree on a function signature. So let's say you update a function signature in the guest binary. Well, now you need to update it everywhere you use in the host. And hopefully you get a runtime error if you don't. So what we were able to do when we also migrated the host from .NET to Rust, we migrated to rewriting our guests from C to Rust. And that allowed us to take advantage of some pretty powerful Rust features like procedural macros to generate code at compile time. And we actually, a colleague of ours, Lucy, implemented a great thing with to define the interface between the guest and the host using with. And so let me go a little more into detail about with. So if you haven't heard of with before, with stands for WebAssembly Interface type. And it's an IDL for defining usually the interface between a WebAssembly component and the host environment is running in. But with doesn't only have to be used with WASM. And so in Hyperlight, you can use with to define the interface between the host and the guest. And the benefit of this is that you'll have a single source of truth of the interface. And then at compile time, from both the host side and the guest side, we can generate Rust bindings for this with, for both the guest and the host side, like I said before. And so if we look at this example, we have a with file right here. And we have a world called greetings demo. And in this world, we can specify the exports that the guests provide to the host, so that the host can use to call into the guest. But we also specify the imports that the guest can expect to use from the host. Because remember, the guest runs without an operating system. So things like getting a current time, for example, is not trivial. So in this example, the guest import from the host is time service. And time service is an interface that just contains one function that returns the current time as a string. And then we also have this export, greeting, which is what the guest exports to the host so that the host can call. And in this case, it's just an interface right here, and it contains one function that takes in a username and returns another string. So given this width, we can create a Rust guest based on this width. So here we have a Rust Hyperlight guest. You can see it's no standard, no main. And the first macro we have on the top of the screen is guest bindgen. And it takes in a path to a with file like the one we said before. And what this does is at compile time, we generate some traits that the developer can implement, type safe traits. So one trait that's implemented is this trait called greeting. We implement it for this struct guest. And there's one function we have to implement because that was part of the with. It's called this greet username, or greet user, which takes in a username as a string and returns another string. And remember that the with also specified what the host provided to the guest, and that was a time service. And so we can call into the host right here on letCurrentTime. And here we just call this Rust function, getCurrentTime. And when this function is invoked, that will exit the Hyperlight guest VM. It will run the host function for getting the current time, serialize the result back into the VM, and the result will be saved in this variable current time. And I think this is very cool because this is a type-safe way. It just looks like a regular Rust function, but in fact, it exits the VM and asks the host for the current time. And then finally, we just return a formatted string given that current time. So this is on the guest, but what does it look like on the host? So similarly, we have another macro, but instead of called guest bindgen, this is host bindgen, and we point it to the same with file as before, interface.with. And because that with file contained time service that the host needs to implement, we codegen, this macro cogens that trait, and we just have to implement it as a developer. So there's this function, getCurrentTime, where we just get current time as a string using the chrono crate, and that's it. And then since this is running on the host side, we need a main function as well to run it. And the first part is just some boilerplate for Hyperlight. But you can see down here that on the sandbox, we call this greet user. And this is codegen from the with file. And when this is called, that will go into the Hyperlight VM, into the guest function we saw in the previous slide. That guest function will then ask the host, what's the current time? And then this getCurrentTime function will be called. And all the results will be serialized in and out of the host. And finally, we get the string back. And if we print it, we get something like, hello, Alice, the current time is whatever. So the main benefit of this with is that we can, at compile time, guarantee that the types are correct. If a function signature changes in the with, well, we get a compiler error. And additionally, since this is at compile time, we can potentially skip doing some runtime type checks that we did before, so we can improve performance as well.
Cool. So we've reached the key takeaway section of our agenda, and we'll start off with some successes of the whole journey. First thing was we got rid of the .NET runtime dependency. Yay. This is nice because with Hyperlight, being a library and us having the intention of it being used by multiple different languages, like for example, you saw just how we had the C API in Rust and how it was used in C#. Well, we could do the same thing with C#. You would have to carry over the .NET runtime with you, which is just not something I think anyone wants to have around with their code. So that was a big plus. And the other one is, might not seem like much, but the maintainers prefer Rust over .NET. So on the daily, just working on the project, it was much, much nicer to have, be working on Rust over C#. And then finally, the promised performance improvement, which looks like this. So again, most of this comes from that garbage collection not existing anymore, although it is not an entirely fair comparison because .NET, it was from our prototype, and Rust is not just that we didn't change anything. There have been performance improvements through features and other work that we've done in the project itself. But overall, our sandbox creation time dropped from 1.6 milliseconds to 1.3 milliseconds with Rust, and calling into the guest dropped from 240 microseconds to 26 microseconds, just like a 10 times improvement. And for Hyperlight, where we have our main things are cloud security, that isolation primitive being really good, and also being able to boot up really fast and execute the guest calls really, really fast. That was just massive for us.
Right, so some challenges we run into. So the first one is that after the migration was done, the Rust API we ended up with was pretty awkward. It was not very idiomatic Rust, and that's mostly as a result of us mostly calling the Rust API from our C API, which was then called from our .NET API. So our Rust API ended up looking very similar to our .NET API, and so we didn't really spend any time designing a nice Rust API, and so that's something we're still working on today, is finding the perfect balance of what a Rust API should look like. Another one we ran into was that it took us a pretty long time to migrate from .NET to Rust. And that was partially due to the fact that while we were migrating, we were also at the same time introducing new features. And so those new features needed to be implemented in Rust, in .NET, and as glue code in the C API as well. And that just made feature work take a lot longer than needed and delayed the migration. So if we were to do it again, we'd probably focus on finishing the migration first and then go for the next nice feature. And lastly, Rust has a famously pretty steep learning curve. I had never worked on Rust before I worked on Hyperlight. So it takes a couple of weeks or months to get used to it. But if you work through it, I think most people who learn Rust don't regret it. And now I think it's a very nice language to work in.
All right, cool. Now, just before we open up for questions, just want to say our GitHub repo is open source. So if you'd like to contribute, contributions are always welcome. Or if you'd like to try using, if you have some potentially untrusted code that you want to run in your code base and you want to consider Hyperlight, we have getting started and documentation and all the good stuff over in that link there. Again, Hyperlight is part of the CNCF. So with that, we have a community Slack in the CNCF Slack called just Hyperlight. You can reach out to us and all the other maintainers of Hyperlight there. And we also host bi-weekly calls going over technical discussions, sometimes demos, roadmap updates, answering questions from just people that show up. So if you'd like to participate in those, we will welcome you. And if you want to find out, again, you can check out our Slack where we post just announcements there of when those are happening, so you can figure out which of bi-weekly weeks it's happening at. Now, just before I open up, quick shameless plug. Again, I am working on this book. I just finished it last month, the last chapter of the preview, but you can currently read it with Manning's early preview, MEEP. And I asked them to create just a discount code if folks wanted to check out for RustConf. So you can scan the QR code, we'll take you to the book, and you can use this code for some discount off of all Manning products. And also for the first 5 questions, I have some free codes for the book entirely. They're 100% off. So we can have some nice questions. You'll get a book for it. When it's printed, you'll be shipped to you. So you get both the ebook that you can read right now and the physical one. So ask us questions. Thanks.
We have 5 minutes.
Okay, 5 minutes for questions. I think we have 3 questions over here.
Wait for the microphone.
Yeah, thanks for your presentation, and that was a real cool technology you're showing. So actually, I'm a bit curious because at the beginning you mentioned that there's no OS inside the hypervisor environment. So is it true that Hyperlight, is that primarily focusing for server-side WASM-like use cases? Because we try to do something similar with WASM, and then the async I/O story is not too great because of lack of a runtime. So how do you solve that kind of a problem inside Hyperlight? How do you do async I/O and that sort of stuff?
Okay, that's a great question. Maybe I'll start, and if you have anything to add. So, well, first thing, Hyperlight does not have async I/O right now. So the function calls to the host, they're synchronous. We have ran an async runtime within Hyperlight, but it's all sort of experimental work right now. Do you have anything you want to add?
No, I think that's it. We don't support any async I/O right now. And yes, Hyperlight focuses mostly on stuff like user-defined functions and smaller workloads like those.
Yeah, but we have a lot of ideas. So right now, the way that sort of guest and host communicates is via shared memory. So we have input and output buffers. So the guest makes a function call, it gets serialized into that region. We'll do a VM exit. Host will read that region, and then can also add onto a separate region input so the guest can read. That doesn't work with async because then you have multiple calls happening at the same time. So our stack or stack pointer onto that region wouldn't work anymore, but we have ideas with ring buffers and some cool technology like that to address it. But there'll be a great point to discussion in the repo or the Slack, because it's something that we want to actively work on.
And this one will be our last question.
Okay.
So my question would be, so Hyperlight is focused around Hyper-V hypervisor, and do you consider support for example, KVM or any other hypervisor so that we can run it on Linux?
Yeah, so we have actually 3 backends right now. We have one, Microsoft Hyper-V. We have Microsoft Hyper-V for Windows. We have Microsoft Hyper-V for Linux as well. And we do support KVM. So we have that as a backend that you can run on Linux right now. Thanks.
All right,
Okay,
I think that was it.
Last question. Awesome. Thank you.